Okay, so you should see the recording right now. So we are continuing from where we left off in the last class, right? So you're looking at higher order functions, and we looked at a few examples um, of higher order functions over lists, such as map and reverse map. Um, so when we talk about higher order functions, we always end up with this one true higher order functions, as I mentioned in the last class, right? And that function is a fold function. And the sort of analogy, if you want, if to compare to imperative programming, is um, fold is a function that is very similar to an iterator, where you can do arbitrary. Iterator knows how to traverse a particular data structure, right? And then you can do arbitrary things using the iterator. And fold sort of nicely wraps the notion of traversal in the function, and it's actually very generic in the sense that um, if I gave you a fold function over any particular data structure, be it a tree or a list or say some B plus tree or so on, you can implement every other function which operates over the tree just using fold, right? So that's we will see some of that in this lecture. So essentially, fold is a function for combining elements from a data structure, right? And it's very powerful. Just as I mentioned, you can experiment, you can express a lot of things with this, and hence it happens to be very generic. And at least I found it initially difficult to understand, like what is going on here. Um, so what I'll try to do is to first provide the intuition for what the fold function is. I mean, it is generic, but we will sort of look at a specific function, and then we will sort of draw the common properties of the function into this generic function. Okay, so without further ado, so here is a function that I can ask you to write, and at this point you might even write, right? So here is a function that simply computes the sum of elements in a list, right? And we want the function to be tail recursive. So what we ended up doing is we have an accumulator, right, that carries the value, and then we have a list. So if the given list is empty, then you just return the accumulator. If the list is non-empty, then what you do is you add the head element to the accumulator, right, and recursively call the function on the tail of the list with the new accumulator, right? So this is what you would write. And we know the initial value of the accumulator. We are doing summation, so the initial value should be so the initial value should be 0. And okay, so if I run this, so I get this function which goes from integer list to integer. And if I run it on a list which has 1, 2, 3, 4, 5, I should get 15. So this should be not surprising, right? So, um, so let's try to break it down, right? So at this point, you can actually write this function. You know enough vocaml to be able to write this. But let's sort of look at what's going on in this function, right? The first thing that's going on here is there is this notion of walking over a list, right, from the head element all the way to the tail. And the way we walk over the list is through this recursive call, where we pattern match on the shape of the list, right? We know that a list is a list of nodes, list of elements, where we have a null and a cons. So we split it apart at every position, and then we simply recurse through to iterate over the shape of the list. So you can imagine, so another analogy would be, so there is only one, there are two ways to walk a list, right? So you can either walk it from left to right or right to left. And for trees, you can do in order, pre-order, post-order, right? Or reverse and so on. So that is what I mean by traversal over the shape of the list, right? There is also this accumulator, right, that keeps track of the current sum so far in this function. There is this plus function, right? This plus function that we apply to each element on the accumulator as we traverse the list. Okay. And the last thing we have is the initial value of the accumulator. So we have sort of 4 broad concepts here, right? So there are of course other things, but I'm sort of picking out things that I want to get the point across. So one thing we can do is we can actually write the same function using list.foldLeft. So foldLeft is a function that traverses the list from left to right and does something on it, right? And in particular, what it does is, let's look at the type of this function, right? The type of this function is it takes a higher order argument, right? That takes two arguments. You can just read it as takes two arguments, A and B, alpha and beta, and then returns an alpha. So what is this argument? So the first argument is analogous to the function that we apply in the previous example, right? This plus function that we are applying to every element and the accumulator is precisely this function, right? Which is applied to the accumulator whose type is alpha here, right? And every element in the list, which is beta here. And this function is supposed to return the accumulator type, the new accumulator, right? So it takes the current value of the accumulator, the current element in the list on which this particular function is being applied, and it is expected to return the same value, same type as the accumulator type, so that this becomes the new accumulator and you can keep going on. Okay, so that's the first argument. That's the higher order function that captures what you are doing on each element of the list. And the second value is the initial value of the accumulator. So this is the same as the 0 that we give here, right? And that is being captured in the second value of the accumulator, the initial value of the accumulator. And the third argument is the actual list that you're traversing over. So the list is a list of betas, right? So observe that in the previous example, we used integer for the accumulator and we were operating over integer list. You're sort of generalizing this idea a little bit, right? So you're saying the accumulator is some type alpha and the list is of some type beta. And the way we connect this alpha and beta is we have this function which takes alpha and beta and returns an alpha, right? It takes the accumulator, the list element, and then gives you a new accumulator, right? This is a little bit more generic than what we had seen in the specific instance. And what does this function actually return? It returns a new accumulator, right? So it just returns the accumulator and we are done. So, okay. Here is the same function again. Here is the implementation of the same function, the sum of elements, using fold left, right? So if I run this, I get the same result, but you can sort of see what is going on, right? The concepts that I said. Fold left internally sort of encodes the idea of traversing over the shape of the list. The only thing that it knows about the list is that it has a particular shape and it has a particular type, right? And fold left encodes how to traverse over the shape of the list and apply this given function, right? Which takes an accumulator, the current element, and then forms the new accumulator. You can sort of see it's isomorphic to what we are doing here, right? We are doing x plus accumulator here. I'm doing accumulator plus x, but it could have been x plus accumulator as well. And this is the initial value. The second argument is the initial value, 0, and that's the initial value here. And the last argument is the list that I'm applying this over. Okay, so what list.fold left allows you to do is sort of encode these functions that you might write yourself using this idea where we split it into, oh, you want to traverse the list from left to right, and what to do at each position, which is this function, what is the initial value of the accumulator and the list. And in fact, the implementation of fold left is very simple, right? So, so here is the implementation. Again, we can sort of compare this to the implementation of sum of elements. It looks again isomorphic. So fold left takes the higher order function, the accumulator and the list. If the list is empty, then return the accumulator. If the list is non-empty, right, first use the function that you've been supplied, this f function, to combine the accumulator and x to get the new value of the accumulator, right, and recursively call the same fold f function on the tail of the list. So the same function, right, new accumulator and the tail of the list. You can sort of see this is isomorphic to this one, right? So here we know what function we are going to apply, which is the plus function. In fold left, we don't know which function, so we are taking this extra argument. Otherwise, it is exactly the same, right? And yeah, so that gives you the desired type. So one way to imagine what happens with fold left is that you can sort of imagine that to be a natural transformation of the shape of the data structure, right? Um, so here is one way to write the shape of a list, right? So you have an empty list, that's a list value, right? And the list with 1, 2, 3, 4, 5 first contains a singleton list with 5, right? And how do you construct that singleton list? It is the value 5 const with an empty list. So that gives you the singleton list 5. And the next thing you do is take 4 and const it to that singleton list 5, right? That gives you another list. And you can keep doing that, right? So you add a 3 to the front and to this list, and eventually you go back 2 and 1, and all you have is this list with the 1, 2, 3, 4, 5. So this is just an illustration of how the shape appears. And fold left, you can sort of understand fold left as first reversing the list, right? So we are going to first reverse the list. So 1, 2, 3, 4, 5 becomes 5, 4, 3, 2, 1. You replace the unit element, right? So if you've done sort of discrete mathematics, you have this idea of unit elements in groups, right? And the unit element in a list data structure is the nil element, right? So that's sort of the unit element. You replace the unit element with the initial value of the accumulator, right? You replace the cons operator, which constructs data, right? So cons takes a value and a list and then constructs a new list. You replace that with the function that is used to compose the accumulator and the value in that list, right? So essentially, what I'm trying to show here is that you can sort of view computations and the data constructors as two sides of the same coin, right? So data constructors sort of construct the data, but they look very similar to what we do when we do computations, right? And all fold left is doing is going ahead and replacing cons with plus, and then replacing the unit element with 0. And of course, it's doing the list reversing, but you can sort of see that this sheds some light into the shape of what fold left is doing. So fold left traverses from left to right, right? And what about right to left? So there is a function called fold right, which traverses from right to left, and it's actually much more pleasing than fold left. In particular, if you can consider this to be the shape of the list, right? Fold right, all it does is take a function f, take a initial value of the accumulator 0, and all it's doing is replacing wherever you see cons, you're replacing that with an f, and wherever you see empty list, it's replacing that with 0, right? And in our case, in the sum of all elements, z happens to be 0 and f happens to be plus, right? And that's the whole idea, right? So you take a shape and you replace the building blocks of the shape with functions and values, and that is computation, right? So I think this is like one of the nicer ideas that you will find in this in functional programming. Essentially, computation is nothing special, right? It's also one way of constructing some shape, right? And it so happens that you can actually compute the result, but that's besides the point, right? So why am I mentioning this? So one thing that we will do when we study Lambda calculus in the upcoming lectures is that Lambda calculus is a very poor language. It has just functions all the way through. And in fact, you can use this isomorphism. The fact that you can encode these sort of shapes with functions to actually construct data types like lists and trees and other things. Of course, Lambda calculus is more of a theoretical exercise, but it underpins all of the things that we are doing with functional programming, right? And the slide is sort of there to show you that we can approach the isomorphism from OCaml to its core concept, but we will also approach it from the other side, where we will start with lambda calculus, which is functions, and we will build things like lists and trees and so on. So you can sort of see that these two things are in fact isomorphic. Okay. That aside, right? That's sort of the philosophy behind fold and so on. So I keep talking so much about the beauty of fold and philosophy and so on, but is it useful, right? That's the question that you need to ask. At the end of the day, you just want to program, right? I want to, as I mentioned in the first classes, um, of course, programming languages are elegant and precise and beautiful and so on, but at the end of the day, they're just tools, right? You just want to solve some problem, and it's like a hammer or a screwdriver. So let's see what it can do, right? Let's first understand fold right. So fold right is similar to fold left. The only difference is that the types look odd, but the concept is the same. So this is the higher order function, right? And the accumulator type here is beta. This just happens to be a quirk of OCaml's type inference, right? So just remember that the list element type is alpha here, the accumulator type is beta, and this higher order function is supposed to return the new accumulator whose type is beta. You take a list, which is a alpha list, and then you take the initial value, which is the beta, and you find when you run fold right, you end up with the final value of the accumulator. That sort of captures the notion of doing computation, right? So fold right is again not special. You can just write it. If you stare at the type, there is only one sort of function you can actually write that satisfies this type. Yeah, so here is that function, right? So it takes a f and an L and an accumulator. So if L is empty, you return the accumulator. Otherwise, you fold right on the tail of the list with the accumulator, right? And then with that result, you call f of x on it. So the reason for doing this is because fold right applies from right to left, right? So you want to apply the function, this f, for the first element as the last thing that you do. So what do I mean by that? This looks weird, right? It's not tail recursive. So that's the first thing that you should observe. And why are we doing this function application last? Because fold right is supposed to look like this, right? For the first element, which is 1, f is applied last to 1, and after all of the computation is done, right? So you finished everything here, and then the last thing you do is to actually apply f on 1 and the resultant accumulator. So this is why the function application looks like this. So complete fold right execution for the tail of the list, you will get a new accumulator value, and the last thing that you do is to combine that accumulator with the element, the first element, right, using f, and you return it. So the thing that you can see is this is not tail recursive, right? So fold left was tail recursive, fold right isn't tail recursive. And fold is, as I mentioned, very powerful, right? So you can implement all the useful functions just with the fold. In particular, here is a reverse, right? And what does reverse do? Reverse takes a list and reverses the elements. And what are we going to do? So think about this, right? So reverse takes a list and returns a list. So, and fold left is going to return an accumulator. So in order for the types to match, the accumulator also has to be a list, right? Because it's going to return a list. And the initial value of the accumulator is empty. And the reason is that if the list is empty, then you just return empty, right? So that's the reason why this is empty. And what happens in the actual function? You get this accumulator, which is the list so far, right? And you get this current element, and you just append x to the front of the accumulator. because fold left is going from left to right, let's take a list which is 1, 2, 3, 4, 5. So initially the accumulator is an empty list. So you will pick one and you will say, oh, create a singleton list with one, and that becomes the new accumulator. And the rest of the list is 2, 3, 4, 5, right? And the next thing you will do is, yeah, I'm doing that, right? So Naman, so okay, so we can try to write it down. So what will happen, right? So initially accumulator will be empty, right? And the list will be 1, 2, 3, 4, 5. Okay. In the first step, we will traverse the list from left to right, right? So we will pick the first element, right? And the current accumulator, and we are going to apply this function, which is accumulator is empty list, and the first element is 1. So the new accumulator is 1 appended to empty list, which is a singleton list with 1. So the accumulator is 1. And internally, what fold left is going to do is to call the same function on the tail of the list, right? So the tail becomes 2, 3, 4, 5, right? You do the same thing again. So consider this to be the accumulator. Take the first element of the list, right? Sorry, first element of the list, and append the first element to the accumulator. So the first element here is 2, and the accumulator is the singleton list 1. So when you append 2 to the front of a singleton list, which is 1, you get 2, 1, right? And you get L equals 3, 4, 5. Because recall that fold left simply keeps applying this on the tail of the list, right? So you keep doing that. And yeah, as you can see, if you keep doing this, right, what will happen? Next step will be 3, 2, 1, 4, 5. And yeah, finally it will be 5, 4, 3, 2, 1, right? Into dot 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 here. And then the list will be empty. And at that point, what does fold left do? If the list argument is empty, it just returns the accumulator, right? And what is the accumulator currently? The accumulator is 5, 4, 3, 2, 1. So that's the reverse of the list, and that's what you get. Does that make sense, Naman? Okay. So if you want to know what's happening, you just take these functions and work through the small definition, right? And write down the values of accumulator and the list values in each step, and then iterate through. That is precisely what I'm doing. And that's how we develop the programs as well, right? So you sort of see what you want for the base case. So if it's an empty list, you want an empty list as an output. And what has to happen for the recursive step? So if you have a non-empty list, what has to happen, right? So you have to take the first element, put it in the accumulator, and you keep doing this again and again from left to right, things will become reverse. Okay, so yeah, so you can work it through, but this is precisely what happens. You can compute the length of the list, right? So because what are you doing in a length, right? You are iterating over the shape of the list, and for every step, you're adding one. So if the list is empty, the result should be 0. So the initial value of the accumulator is 0. And at every step, right, I don't care about what the value of the element is, because you don't care, right, for computing the length. And at each step, you just say accumulator is accumulator plus 1, right? And that gives you the length of the list. So observe that I have not done anything interesting, but I sort of just wrote on the program, and I get the most useful type, right? This length function can be applied on any list, right? And I didn't have to specify anything special to get this generic length function. It just falls out naturally. And the result is an integer. You can, in fact, implement map just using fold, and in particular, we are going to use fold right. And the reason is that so when you want to take the, so just like what happened with reverse, right? Reverse took the leftmost element and kept pushing it into the accumulator, and what you ended up is the reverse of list. But if you start from the right and you kept doing it, you'll get the same list, right? So if you start from the left and keep pushing an element into the accumulator, you get the reverse of the list. But you start from the right, you kept pushing into the accumulator, you'll get the same list, right? So we want the order of the elements to be preserved. But what map does is at every step, right, it maps this function f, this higher order function f, on each of the element, right? So you apply f on each element x, right? So recall map in the last lecture. All it does is if the list contains a1 to an, and map function says the higher order function is f, and the result is just going to be f applied to a1 semicolon f applied to a2 semicolon f applied to a3 all the way to f applied to an, and this is precisely what is happening here, right? So I'm at each step, all I'm doing is applying f to x, and then like appending it to the accumulator to create this new list. I'm doing it from right so that the order of the elements in the original list and the resultant list is preserved. Okay, so yeah, I haven't written fold right. So this is fold right. So yeah, so you get the right type for map, right? So it takes a function that maps from alpha to beta. You give it an alpha list, it returns a beta list. I want you to go through these and convince yourself that this works, right? Work it out for each step. The observation is that map function is not tail recursive because fold is not tail recursive. We saw this earlier, right? So when I introduced map function, I mentioned that map is not tail recursive. It sort of follows from the fact that fold right is not also tail recursive. Yeah, okay. So what else should I want to say? The observation is that any function, so any function that you want to write on a list can always be written with a fold, right? So you never have to write any other function for traversing over the list except fold. But sometimes we, for convenience, we just pattern match and write our own functions by hand because it is readable. But in fact, you can write any function using fold, right? So here is an exercise for you. So implement a function exists, right? That takes a predicate, right? So it applies to, it's a function p, which when applied on an element returns true or false, right? You take a list as an input, and the function should return true if an element E exists in L such that P of E is true. So when you apply P to that element, it should be true. So here is an example, right? So what I expect is I'm using exists to search for an element. I'm using exists to check whether the list has an element 0, right? So the predicate is E is 0. So it's the element 0. And if I apply it to 130, it should return true, right? And you can, what I want you to do is to implement this with the fold. Okay. And yeah, so this is another exercise for you just to get more practice. Implement append function, which takes two lists, right? L1 and L2, and the result is going to be the concatenation of L1 and L2. And here is an example. You can also implement it using fold. Use fold right to implement this. And the reason is that we want to preserve the order of the elements, right? So the intuition is the same as what we had done for map. Okay. And that completes the higher order functions lecture. Do you have any questions? I'll just stop for a minute. and you can ask me any questions. Again, fold is sort of fold takes a while to get your head around, right? It might click for a few of you, but it didn't click for me. But once you sort of see that everything is a fold, you can sort of see fold everywhere. And yeah, the implementation itself is not complicated, but it's the often you have a very powerful abstraction. It is knowing when to use that abstraction, right? So that's really going to be the question, and it comes with practice. So we'll do a few um, we'll do a few assignments which sort of gives you this idea. Yeah, so it does have or and and. So the question is, does OCaml have or and and? Yes, it does. So true and false, right? And then okay. Any other question? Sir, if you want to do something more difficult like a minus, good question. So you can encode this fact in the you can encode this fact in the accumulator, right? So you keep replacing the function. You keep changing. I mean, abstractly it's flipping, right? So at every step, initially it is negative, then positive, negative, positive, negative, so on. So the idea is that this accumulator should sort of take this idea of initially there is going to be one function, and then it can be, yeah. So you just, yeah, that's what you do, right? So I would just yeah, true or false or something. There are multiple ways to do it, but that's really what you do. So every time you recursively call, you just flip it, right? And flip the sign and keep doing. You can do so. Just teasing with terms, but actually terms don't mean anything, right? So this in programming language theory, fold function is known as a catamorphism. So the idea is that it tells you how to traverse a particular structure, right? The structure can be any data structure. It just tells you how to traverse that structure. And it is a known result that if you have a catamorphism, then any sort of computation can be encoded with that catamorphism, right? So, and the practitioner translation of the definition is, if you have a fold, you can implement anything, right? So there is no function that you cannot implement with the fold. Okay, so you can also ask questions on Slack. I will try to answer questions there. So what I will do now, so what we've so far seen is we sort of dived into OCaml, right? And I've been teaching you some concepts as we went along, while also introducing the language, right? So for a change, what we will do in the next few lectures is actually, with the accumulated knowledge that you have, we will study the earliest and the simplest programming language. It happens to be a functional programming language. We'll just study the simplest functional programming language, which is Lambda Calculus. And we'll sort of tie a lot of the concepts that we've studied here back to what Lambda Calculus will do, right? So you just pattern match on it. So Raghu has a question. So is there a way to access the nth element in a tuple? You will have to pattern match, right? So if you know that there are 7 elements, then you need to have a pattern which is 7 tuples, include 7 elements, and then you just extract the 7th one. You cannot So what Raghu is asking is a very interesting question, right? So can you have a nth of a tuple? And this is, I'm not going to give you an answer, but I'm just going to ask you a question, right? So can you write a, does there exist a function where you can sort of say, right? And actually, I can't even write the type of this function, right? So if you want to extract the nth element of a tuple, and we know that a tuple can have different typed elements, right? So if I want to extract the first element from this, and I'm taking an arbitrary index here, the return value is in fact dependent on the type of the return value is dependent on the index, right? So if the index is 0, then the return value is quote A. If the index is 1, then the return value is quote B. You cannot write this function in OCaml as it is. Actually, we will see in later lectures, we will sort of see how to encode something similar using a higher level feature of OCaml. But just to tease you with an idea, right? So the problem here is the type of this function, right, is dependent on the value. And programming languages have this concept of value dependent types. So the type of this function is dependent on the value, because if this is 0, then you get an quote A, and if this is a 1, you get a quote B, right? This concept is known as dependent types, right? And there are research languages that have dependent types in them. We will study a very rudimentary support for dependent types in OCaml when we study GADTs in later lectures, but you cannot write this type in plain OCaml, right? Okay. Okay. So anyway, so enough of digressions. I want to move on to Lambda Calculus, right? So we'll sort of see why Lambda Calculus today, and we might then come back to the actual mechanics in a later class. Okay. So, okay, Lambda Calculus. So we are going to, we'll study a few lectures on Lambda Calculus. I think it's quite interesting in its own field of study, right? Just studying Lambda Calculus is interesting, but we'll sort of tie it back to practical functional programming, right? So that you can use these concepts elsewhere as well. So, okay. Oh, this is all. So, okay. So back in the 1930s, right? So really, there is this big question about what is computability, and I am not going to delve deep into the question, but informally, what it meant is, what does it mean for a function, right, that goes from natural numbers to natural numbers to be computable, right? And there were 1930s was a brilliant period where several brilliant scientists were mathematicians, essentially were working on the same problem and making independent progress, right? And they sort of made revolutionary progress, which sort of underlies much of the computing that we do today. And informally, the question of what it means to be computable is, right, if I gave you a pen and a paper, you should be able to tell me what is the result of f applied to n for any n, right? That's really what you mean by computable. Actually, the difficult bit here is to define formally what a computable function is, right? And three different researchers attempted to formalize computability. Actually, once you can frame the definition formally, the rest of the things will fall out naturally, right? And the problem here is just framing the definition. So the first of those mathematician scientists is Alan Turing, right? So he defined the idealized computer called the Turing machine. And what Alan Turing said was, if a function is computable, if and only if it could be computed by a Turing machine, right? So this is his definition. So what he did was he described what constitutes a Turing machine, and he said, for a function to be computable, it must be the case that it can be computed by a Turing machine. And a lot of the current programming language technology owes to Alan Turing. And we have this concept of Turing completeness in programming languages, right? And we say that a programming language is Turing complete if it can map every Turing machine to a program, or you can write a program that simulates a universal Turing machine in the programming language, or it is a superset of a known Turing complete language. And typically, the way we show that a programming language is Turing complete is the second one, right? We just write a interpreter for, we just implement a universal Turing machine in that programming language. And most of the languages that we use in practice today, right? Most of the programming languages that we use are Turing complete. There are several, if you read the Wikipedia page of Turing completeness, you will see a lot of hilarious instances as well. There have been instances where systems, right, not even programming languages, just systems, some constructions, right, artificial constructions have ended up being Turing complete completely by accident, right? And a famous example is, yeah, PowerPoint is Turing complete. Yeah, that's right. And C++ templates are Turing complete. You can write entire programs, right? You can write every program just in C++ templates. What does this mean? I mean the template compilation, right? What the C++ compiler does in order to compile a program that has a template use to produce a binary. The compilation itself is Turing complete. Yeah, so there have been a lot of games which are Turing complete. You can have a look. It's quite hilarious. While Turing was making revolutionary progress, right? Alonzo Church was also working on a similar question. So Church developed this idea of Lambda Calculus, right? A formal system for mathematical logic, right? And he postulated that a function is computable if and only it can be written as a lambda term, right? And Church was Turing's PhD advisor, right? And Turing later showed that Church's definition of lambda calculus and his Turing machines were in fact equivalent. So this came to be known as Church-Turing Thesis. And the third person is Kurt Gödel, right? So Gödel was working on the same definition, and he defined this nice framework where he said, without going into details, it contains a class of general recursive functions, and he postulated that the function is computable if and only if it is general recursive. And it is now known that all three definitions are equivalent, right? So, and so Church-Turing thesis is in fact one of the most important ideas in computer science, right? So, sort of revolutionized the very idea of computing, right? And the idea goes far beyond just the thesis. But if you sort of look at even though we've known for a while that these two ideas, in particular this lambda calculus and this Turing machines, are equivalent, in contemporary computer science research, right? Computer science as an area, these two happen to be concentrated by two different specializations. In particular, Turing machines are used a lot by folks who work on algorithms and complexity, but Lambda Calculus is the go-to tool for programming languages people like me, right? And this particular dichotomy is not accidental. So Turing machines are quite low level, right? So they involve a tape and a pointer and what happens at each step and so on. So they are well suited for measuring efficiency, right? Resources and efficiency. Whereas Lambda calculus, as we will see, is quite high level, and it is useful for abstraction and composition. Essentially, what it says is how do you organize your program, right? And how do you take those individual pieces and put them together? So Lambda calculus happens to be um, the the core principle on top of which all of the functional programming languages are built. And in fact, Lambda calculus gives you enough features that all that we are doing in OCaml and so on is just you can sort of think about them as just making Lambda calculus practical, right? So and yeah, so in fact, Lambda calculus is as powerful as any programming language, right? So um, it is in fact so small. It is the smallest Turing complete programming language, right? So it only considers three instructions, right? There are only three forms, production forms in Lambda calculus, and it can express all the features that you can find in modern programming languages. And what we will try to do in the next series of lectures is to show how you can sort of encode these wide variety of features, right? Multi-argument functions, for loops, while loops, heaps, and so on, just using Lambda calculus. And at its core, all Lambda calculus does is functions, right? And all you need is just functions. And it doesn't have anything else. Actually, it doesn't have a notion of branches. It doesn't have like values. I mean, it has values. The only value is a function, and the only thing that you can do with the function is apply it, right? So it's quite surprising how you can encode all of what we do in modern programming languages using Lambda calculus, right? So of course, we don't write programs in Lambda calculus today and execute them because that would be inefficient. But the point of studying Lambda calculus is to get to the essence of what programming is, right? And where these features are, why these features come from, what is primitive, and so on. And in fact, Lambda calculus is precisely defined here. This is entire Lambda calculus, right? And I don't know why all of this is a little bit off. So I'm describing a grammar here, right? And um, I believe that you're studying compilers as well, and you might have come across abstract syntax tree, right? So this is sort of describing how to construct terms in a Lambda calculus, right? And there are only three ways you can construct expressions in Lambda calculus. So the expression could be a variable, right? The expression could be an abstraction. We call it abstraction, but you can sort of imagine an abstraction. When you have lambda x dot e, you can read it as OCaml for fun x arrow e, right? Here is a way of defining anonymous functions, right? And this is precisely defining that anonymous function where it takes a single argument x and the body is e. And the last thing you have is application, right? You can take a function, you can apply it to a value. And these two are so this could be more complicated, right? So it need not be just lambda here. It could be itself an application, for example. And this is all of lambda calculus syntax, right? And yeah, so there is nothing but higher order functions here. So we have functions. We can pass around functions. We don't even have zeros and ones. We don't have true and false. We just have the syntax, right? And I'm going to try to convince you in the next 2 or 3 lectures that you can, in fact, encode a lot of the things that we've studied so far, right? We've not studied a lot in OCaml, but we've studied a substantial bit of OCaml. And I'm going to tell you that you can express all of that using just these three productions, and we'll see how that how we can do that in the next couple of lectures. And I think I'll stop here. Yeah. So any questions so far? I think we've sort of looked at the motivation, and in the coming classes, you will actually play around with lambda calculus, right? So this Jupyter notebook includes a lambda calculus interpreter, so you can actually think about these as building blocks, right? So you have Lego, right? Lego has different colors, but if you sort of stare at it, it has a single template, and you can construct arbitrary shapes using a Lego. And I hope to provide you the same experience with this, right? These are like building blocks, and using these building blocks, you can manipulate them in the interpreter. You can actually write lambda terms and see them evaluated, so that you'll sort of appreciate why lambda calculus and what power it has. So no questions. I'm just staring at questions on the side. So I'll stop here. I think I'll let you go, and then we can meet next week. Thanks, everyone.